Welcome back. Thank you. So, yes, indeed, thank you for that hand signal and omitting the middle one. So I think what's really fascinating to me is the science fiction and science fact, and that's what we're going to hear about today. I'm really excited that we have a really true expert, someone who builds rockets and satellites and sends them out into space. And what I find interesting in the comparison is that science fiction is really, and shows like Star Trek and others, really tell us something about, makes us think about what might be possible in terms of exploring space and how far we can go and where we could go. It really fuels the imagination. But I think it's also really important to stay grounded, not in just science fiction, but also in science fact, so that we know what is actually and truly possible and doable and what has been done. So that's what's really neat about today, is that we have the director of the Texas Spacecraft Laboratory, and a number of the participants in that laboratory, students and otherwise, are here today. We're going to hear from the director. So not only do we have a true rocket scientist, but this rocket scientist directs this lab that has actually won a number of awards for the satellites that they've designed. So it's one of the leading laboratories in the world for building these sorts of spacecraft. And at the same time, the person you'll hear from is also an award-winning teacher. He's a member of the Academy of Distinguished Teachers at the University of Texas. A very small percentage of teachers at the University of Texas are members in this distinguished academy. So we're really in for a treat. Still waiting for the thumbs up. And do we have a thumbs up yet from the back? We have a thumbs up. Okay. Well, let's go ahead with the first video.
Space, the final frontier. These are the voyages of the Starship Enterprise. Its continuing mission:
to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.
Still exciting. Okay, and now I'd like to thank a lot of the people who helped put today's event on, including all the people who, if you're upstairs in the ballroom on the second floor and you went into the planetarium or created a rocket ship, all of these people helped with this, and let's hear it for their efforts. Really, it was a lot of fun. Okay. Next slide. And also thanks to the Environmental Science Institute, the staff, the interns from UTeach, and the Environmental Science major student volunteers, and all of our co-sponsors here at the University of Texas. Okay. And we are very proud to present the 89th in this series, Hot Science Cool Talks. And the title of the talk is... But before I reveal that to you, please turn off all your electronic devices. And remember, there's no talking during the presentation. There'll be ample time for Q&A afterwards. We start at 11, we end at 12:15, and tonight we're going to hear about space exploration from science fiction to the Texas Spacecraft Laboratory. And as I told you a few words about the laboratory, I'm going to let Professor Glenn Lightsey regale you with all the amazing things they're doing. But I don't know if spacecraft laboratories have logos or mottos or things like that. But I think if they did, for the Texas Spacecraft Laboratory, I'd like to offer one. It would be send spacecraft, go boldly where no spacecraft has gone before. Live long, hook 'em. All right, please welcome Professor Glenn Lightsey.
Thanks, Jay. All right, hi everybody. Welcome to Explore UT. Is my mic okay? Good. You all ready to go exploring? It's cool. It's going to be a really good day. I think the clouds, a little cloudy, going to burn off, and then it's going to be beautiful. And you're going to be able to go all over the University of Texas. It's amazing. There's all kinds of incredible things to see and do, and take advantage of it. Walk all around the campus. It's science is a lot of science stuff, but a lot of other stuff too. So you can really learn a lot about the university and what we do here. So I'm going to talk today about another kind of exploration, which we're going to do, which is space exploration. And the title of the talk is From Science Fiction to the Texas Spacecraft Lab. And so I'm going to tell you about some things just about space in general that I think everybody is interested in. And then also, I'm going to talk about our lab and what we do here at the university as research, because a big part of our university is doing research and why we're interested in that research. So this picture, which is on the cover, actually has some meaning to us in the lab, because this is one of our satellites. This is actually taken here on campus, and these are our students. These are undergrads, mostly. I think everyone in this picture is an undergrad. And they're watching a satellite that they built being launched into space. This was launched out of Kodiak Island, Alaska in 2010. I'll be talking about that a little bit later, but it's pretty cool. It's pretty amazing. I mean, it's one thing to watch a launch. Everybody should watch a launch if you have the opportunity. But when you watch a launch that something you built is riding on that rocket, that's a pretty cool feeling. So it's been great that we've been able to do that here at the university. Of course, we are rocket scientists, and you're all rocket scientists too now that you're here. And that means that, among other things, we are the subject of a lot of jokes, and it is a lot of fun. Hopefully, this is not going on in our lab too much. Although sometimes, we have to solve a lot of hard problems, and we feel kind of like this guy, pulling when he should be pulling. And our rockets are supposed to look like that, but sometimes they look like that. And then we have to deal with this guy, right? So a lot of people say, do you watch The Big Bang Theory? And I was like, well, I don't have to watch it because I live it, right? So all those things that are like funny to everybody else, that's my real life. So it is rocket science. How did I get here? How did I get to the point where I do this all day long? I work on rockets, and I just can't get the grin off my face because it's like, I get paid to do this. How does it happen that you end up in this kind of a job? And for me, if you just think about what you saw when you were growing up and how that kind of affected you as you were growing up, these are the kinds of things that I saw. I pretty much grew up in the 1970s, and all these images were around me. And so, I saw things that were science fiction. I think I watched every Star Trek episode. So I've got the button on. I'm an engineer, Star Wars, all these great movies which are part of our culture. But also at the same time, I saw all these real things happening which were pretty incredible. I mean, the fact that people put a go-kart on the moon and rode it around, that's pretty amazing. The fact that we sent a probe to a place like Jupiter, pretty amazing. This kind of a picture, it's amazing to see a person floating out here by themselves. This is not a scene from the movie Gravity. This really happened. But and here in the middle of it all is Carl Sagan. He's the guy that really inspired me and a lot of people like me with his series Cosmos. And they're redoing that series with Neil deGrasse Tyson. And so I really encourage you to watch that if you're interested, if you're growing up and you're interested in math and science. But also because you have all this happening at the same time, it's easy to get a little bit confused. The lines are kind of blurry. between the things that we've actually done and the things that just sort of happen in the movies. And so it's kind of good to calibrate ourselves, like how do we know what is real and what is just sort of imaginary. Today, things are not too different, really. These are the kinds of images you're probably seeing today. It looks like the Enterprise got an upgrade, actually, in the last 20 years. And, we have a lot of movies that people like to watch, but we also have a lot of really cool, real things happening. I mean, we have our own go-kart on Mars now, except this go-kart isn't driven by humans. It is, but remotely. There's nobody riding on it. They're commanding it through a computer. We have the International Space Station, permanently orbiting the Earth, and lots of astronauts basically living on there. So pretty cool that all these things are happening all around us. Again, some things are real and some things are imagined. So what I'm going to talk about today, I've got kind of 3 parts of my talk. I'm going to just talk about, I call them space myths, some things that I think are interesting about space that I think you'll be interested in too. Then I've got a section called Are We There Yet? I'll talk about this because I think the scale of space is really interesting. It's just so big. It's way bigger than we can really imagine, and I think that's a good thing to talk about. And then I'm going to end up talking about our research, what we do here on campus at the University of Texas, and we actually build satellites and launch them into space. It's pretty cool research. So first of all, I've got some myths, and I want to start with something. I want all the young people in the audience to answer this question for me, okay? So the myth is, or it's a statement. Complete this statement. And I want you to shout it out, all right? So the Earth orbits around the sun. Yes, you got it right. I'm so proud of you. Because actually, all the planets in our solar system do orbit the sun. Believe it or not, this question was asked on a questionnaire by the National Science Foundation last year, and 25% of all Americans could not answer this question. Is that amazing? That's really surprising to me. So first of all, congratulations to all you people who shouted it out. You already know something about science that 25% of your fellow Americans could not answer. But it also really points to the need for basic science literacy. We really need to make sure that certain facts about science are really educated or communicated to everyone. And we can't take for granted that this stuff is just innately known, right? So it's important to tell everyone and to share science with everyone so we can, so we can all be smarter. Okay, here's another one. There is no gravity in space. We've got a picture of these guys. This one might be a little harder. They're all floating around in the space ship, and they're all having a good time. The girl's hair is flying up, right? So no gravity, right? What do you think? It's a trick question. I heard both true and false. So actually, everything has gravity. Everything that has mass also has gravity. Even when you're in space, there's gravity. This map is actually made of the moon. This is the moon's gravity. And you can see crater impacts and things like this. It's a really precise map of the moon's gravity. It was just recently made, within the last couple of years, a mission called GRAIL that NASA flew. They flew an orbiter, 2 orbiters actually, around the moon and made this gravity map. Why are these people floating if they should be feeling gravity all the time? Any thoughts? Well, they're in orbit around the Earth, and the spacecraft is actually in orbit around the Earth with them, right? All of these objects are in orbit at the same time around the Earth, and since they're all moving together, you get that sensation of floating. But they're absolutely feeling the Earth's gravity. In fact, in low Earth orbit, the Earth's gravity is like 90% of what it is on the surface of the Earth. So it's just that they're in orbit and we're not. We're standing on the surface of the Earth. Okay. We see so much science fiction movies, and it's bread and butter that you just push the warp drive button and then you go to another planet, right? Is faster than light travel possible? No, right. Yeah, I hate to rain on your parade, but faster than light travel actually breaks the laws of physics as we know them today. Now, I want to be careful about that. They say never, right? And it is cool to think about faster than light travel, and it would change the way we understand the universe. But in order for that to happen, someone is going to have to basically have some discoveries that really haven't been made yet. So just because you see it in the movies, it doesn't really exist today. That actually is important because when I talk about the scale of the universe, which I'm going to talk about in a minute, we have to think about it in terms of what we can actually get to, which is, we travel a lot slower than the speed of light. Okay, here's myth number 4. NASA consumes 25% of the U.S. budget. Do you believe this? True or false? In a survey, which was not that long ago, I know it seemed like a long time ago to the young people, but this was the most common response. There's a big disconnect between what people think NASA consumes and what it actually does in resources. This is the truth. The truth is that this little sliver is the portion of NASA's budget compared to the rest of the U.S. budget. And in fact, it's less than 1%. It's less than 0.5%. And in fact, if you tracked NASA's budget over the entire life of NASA, which has been a little over 50 years, it is now at the lowest level percentage-wise it has ever been since the first year that NASA was formed. So NASA's budget has actually, relatively to the U.S. budget, has been shrinking, even though maybe in absolute dollars it's stayed the same. And I think we need to understand this. First of all, we need to understand that the space program is not something you should take for given. It exists because we as taxpayers want it to exist. And we need to be advocates for the space program if we think it's important. There's no guarantee that it will be there. It could just be zeroed out. It wouldn't take very much to make that go away completely, right? So we have to be proactive in keeping the space program going. It also shows that, hey, look, there's a lot of financial pressure because there's all these other important problems that the U.S. government has to solve, but there's a lot of pressure on keeping costs down. And so we're always looking for better and more efficient ways to do things, and this is actually something that affects our research that I'll talk about in a minute. So those are just some basic space myths. Now, I want to talk about this topic, are we there yet? This is just, I think this is interesting. So first of all, what is space? Okay, we think about space, we think about stars, and it's dark, and space is everything. Space is all around us. When I'm walking from here to here, I'm walking through space, right? The outside, this tree, this is all in space, just like a planet is in space. So you're all in space. And we actually live in a part of space that humans can survive in, but our part is actually really small. The habitable zone of what humans can live in is just this narrow ring that goes around the surface of the Earth. And if you climb the highest mountain, you can't actually survive because the atmosphere isn't dense enough for you to get enough oxygen. So most of space is not habitable, even on the Earth. And as far as we know, no other place is known where humans might live. So the Earth is pretty special, and this is why we have to think about our environment and protecting it for future generations. But we do see evidence of other planets and other planets that might be Earth-like. And there are spacecraft that NASA has built. Kepler is the name of a spacecraft that have found actually now hundreds of planets. This is a new fact. I mean, 10 years ago, we could only say maybe there were planets. But now we have evidence that there are planets and other stars. And if there are other planets, maybe there are some Earth-like planets. That's pretty interesting. Wouldn't it be cool to go to those planets? So we'll talk about that. So what is a spaceship? Well, really, a spaceship, if we talk about space, a spaceship is really something that surrounds and protects the cargo inside, and presumably you can move around in. Go outside and drive in your car. Your car is a spaceship, right? Because it's moving you through space, just that space is on the surface of the Earth, right? So you want to see a spaceship? Just go get in your car, right? The Earth is one example of a spaceship. We just don't think of it that way, right? It's moving us around through space. But we don't have any ability to maneuver it. So I think you know what I mean. What would a real spaceship look like, right? Would it look like this? And what I want to do today, hopefully, is kind of broaden your perspective on what a spaceship really is. We've talked about a really big spaceship like the Earth. We're also going to talk about a small spaceship that you can hold in your hand. Okay, another interesting idea is because people know that space is really big, they typically think it's also really far away. When we talk about space, and I'm changing my definition really, we think about that empty place, right, that you can go to that's above the Earth, and you can look down on the Earth. And we know that space is out there. We have to, even though there's most of the time nothing there, we still have to be able to go through it to get somewhere. And most people think that, because it's far, it's really big, it must be really a long way to go to get there. Actually, it's not that far. space station, which orbits over our heads, you can actually see it at sunset and sunrise sometimes when the light is right over Austin, is only about 400 kilometers. I'm going to challenge you guys to think in metric units here. But that's about 200 miles, and it's really just the distance from Austin to Houston, right? So imagine driving from Austin to Houston. You will have driven the distance. The people who came here from Houston today actually drove the distance to the space station. They just did it on the surface of the Earth. You'd have to drive in the vertical direction to actually get to space station, and that's the hard part, right? Because you've got to be fighting gravity the whole way. But space is actually really big. It's really big, much bigger than that. Just getting to space. And I want to try to put this into context. So let's imagine something that some of us have done, which is fly from New York to Los Angeles, and you get on an airplane, and you're on the airplane for a pretty long time, like 5 or 6 hours. And during that time, you will fly 4,000 kilometers over the surface of the Earth. That's about 1/10 the way around the Earth, by the way. And we're going to use that as our metric. So first of all, how far away is the moon? What do you think? Pretty close by. It's our closest neighboring object. It actually orbits the Earth. Now, I need a volunteer, okay? I want a kind of a young volunteer. So who wants to be a volunteer? So here, why don't you guys on the front row, you guys duke it out and decide who's going to be. Or you can both come up. So what's your name? Come on around. So I have an Earth. This is pretty cool Earth, right? It's a basketball Earth. I can, like, jam the Earth through the hoop, But this Earth is a basketball. Okay, since there's two of you, tell me your names. Julian?
Julian.
Uh-huh.
Hank.
Hank, okay. Where do you guys go to school?
Breaker Woods.
Breaker Woods, all right. Awesome, not too far away, right? Okay, who wants to hold the Earth?
I do.
Julian gets the Earth. You've got the whole Earth in your hands. I hope you feel strong. Hank, you got the moon? That's the moon. Glows in the dark. All right. So, Hank, why don't you hold the moon where you think it should be relative to the Earth? Yeah, like there, maybe? Closer, further away? Space station on this scale would be really close to the surface of the Earth. Okay. So, audience, what do you think? You think that's right? Or too close, too far away? Maybe too close? Okay, so Hank, I want you to walk a little bit further away to take the moon with you. And I'll tell you when it's about right. Keep going. Stop. Nope, keep going. Keep going. Watch your step. Keep going. Okay, about there is where you can stop. This is actually the real scale. On this scale, if the Earth is this size that Julian's holding, I got Antarctica upside down, got the Earth upside down, then the moon is about 30 feet away. Okay, so this is the entire Earth. Okay, this is thousands of miles around. You have to go around the Earth, and this scale, the moon, which is our closest object, is 30 feet away. So across the room on this scale. Okay, thanks, guys. Hank and Julian. Thank you. So, let's see what I did here. So, I'm just going to say what we just demonstrated, assuming I do it right. That is a two-scale picture, which we don't often see, of the moon and the Earth. And you can see that the moon is actually really far away compared to the Earth. Thank goodness, because we wouldn't want it like crashing into us or doing anything if it was too much closer. That's about 400,000 kilometers, and that distance doesn't really mean a whole lot. So remember the cross-country trips? That's 100 cross-country trips in the vertical direction. Now remember, we said it takes about 6 hours to fly just on the surface of the Earth across the country, 4,000. So you take 100 of those. Now you can start to see that just getting to the moon, if you could fly there in an airplane, which you can't, of course, it's a different problem because you're out in space, but it's going to take a few days, right, at our speeds. It's not going to happen in a few hours. And that's what we've experienced as the astronauts that went to the moon. You can go to the moon, and we've been to the moon. And we have 12 humans that walked on the moon, and sadly, they're not all still alive. So hopefully we'll be able to go back soon. This is just an incredible picture. I love this picture because This is the Earthrise over the moon, seeing it from the moon's perspective. And then in the front, you have what will be the lunar lander, right? This is going to land on the moon, and you're taking this picture from another spacecraft. So we have two spacecraft with astronauts on them, a human spacecraft. We've got the moon and the Earth all in one picture. Pretty amazing picture that was made there. Okay, but we want to go to planets, right? So I've got Mars over here. Mars is a little more exciting than it's a soccer ball. So who wants to go to Mars? Okay. Well, I will tell you, I hope you brought your track shoes. Because if you want to go to Mars, do we have any runners in the audience? You're going to have to run a 10K. Because on this scale, in one direction, not out and back, on this scale with the Earth, I can hold it in my hand. This is obviously a pretty small scale. Getting to Mars, and we have to go around the sun to get to Mars because we have to use the sun's gravity to get to Mars, is 500 million kilometers. And that on this scale is a 10K. So next time you want to run a 10K road race, take something like this with you and say, okay, I'm carrying Mars. I'm going to Mars. And when I get to the end of my 10K, I will have run that distance if the Earth was the size of a basketball. So see, these distances are really pretty huge. And we start, even cross-country flights, we start seeing that we get big numbers, 133,000 cross-country flights. Now you can see that getting to Mars is going to take you a lot longer, like years, a year to get out, a year to get back. And the real issue with going to Mars, it's a different kind of problem than going to the moon, is how do we keep astronauts alive the whole time? What if we wanted to go to other planets like Neptune? Neptune is the farthest planet in our solar system. Sorry, Pluto. Didn't mean to, but you got demoted. But, Neptune is another 10 times further away than Mars. It would take more than 1 million cross-country flights just to get to Neptune, and this would take years. And we have actually sent a probe to Neptune to take this picture, but only one, right? Because it's hard to get there. But, what if we really wanted to go to a star? Well, just our nearest star, Alpha Centauri, is 4.5 light years away. We don't even really think about that in terms of distance, but light travels really fast. You think of it as instantaneous, but it's not. It travels 300,000 kilometers per second, and you can measure that. To go 4.5 light years, the amount of time that at this speed you would go in a year times 4.5, that is 8 billion. I got to say billion, see, I'm proud, like Carl Sagan. 400 million cross-country trips. I can't even think of that, right? That's just the nearest star. So let's pick the fastest satellite we know, the Voyager probe. That's left our solar system. And it's traveling about 17 kilometers per second. That's 38,000 miles per hour. That's pretty darn fast. Even that probe, if it was going in the right direction to get to Alpha Centauri, which it is not, it would take 75,000 years to go that distance of 4.5 light years. That's more than the entire history of our civilization, right? So, just going to the nearest star, it's something with our own technology we're really not going to be able to do anytime soon, right? So we need to focus on the planets, the things that are nearby that we can do. So, there's just some basic information I think that's interesting to everyone. Now what I want to talk about is our lab and what we're doing in our lab. First of all, I want to talk about who we are in our lab. Our lab is myself and a lot of students, undergrads and grad students, and some of them are here today. So you guys who are from the lab, why don't you raise your hands. So there's a row of them right there. So these are the guys who do the actual work. They're the real rocket scientists. The professor is the person who just gets you into trouble, and then the job of the student is to get you out of trouble. So they get me out of trouble all the time. We've built satellites, and this is a picture of our team. Not all of our team, but some of our team that was part of that activity. And we won a national award for the satellite we built. And because we won the award, the students were kind of joking around, saying, hey, let's get the UT Tower lit, And we started thinking about it. They do light the UT Tower for football and basketball national championship. This is kind of the same. So why not have them light the UT Tower for us? So I actually asked the aerospace department, how do we get the UT Tower lit? Nobody knew, right? It had never been done that they lit the UT Tower for engineering. And sure enough, we wrote a letter to the president of the university, and they lit the UT Tower for us. So this is a picture of us with the UT Tower. So what do we do in the lab that they would actually light the tower for us? Well, what we do is we build satellites. We design satellites. We do the whole process. We even write proposals. And those satellites are funded. They're funded by NASA and the government, the Air Force, with that 0.5% we get. And we build these satellites, and we actually get them flown in space. This is not a Photoshop or anything. This is an actual picture of a satellite we built in space. And these are not necessarily the big satellites you might think of. These satellites are this size. You can hold them in your hand. Now, this is a model, right? It's a plastic model. But this is the full scale of what these satellites are. So, is that a satellite, and what can it do? Would be an interesting question. Why do we do this? Why do we think this is an important problem to work on? First of all, we are all, as aerospace engineers, we're believers in the space program and in space exploration. We think that at some point, hundreds of years from now, people will look back and they'll say, that's when our civilization became a spacefaring civilization. When will they say that happened? And what is our role in making that happen? What we know now is that getting to space is hard. It takes a lot of energy. It's dangerous. It's expensive. This is why we don't do it more often. And so what is our role in all of this? Our role in this is to try to make space more accessible, not just for big government agencies, but for everyone to be able to fly their spacecraft in space and do science. So this is what motivates us. Now, why is going to space so hard? Well, like I said, it takes a lot of energy. You've got to overcome gravity, and so you build these really big rockets. And this is a huge thing. You wouldn't want to be around it when it's doing this. It would singe the hair off your head. So maybe that happened to me. I don't know. But this is what a spacecraft typically looks like. This is the Mars Curiosity rover. The rover is actually inside this thing. This is the aeroshell that keeps it protected when it enters the Martian atmosphere. And this is a really big thing. I mean, look, here's a ladder, here's a computer, and just roughly, to within a factor of, 2 or 3 or something like that, getting anything into space costs about as much as that, solid gold. Solid gold costs about $40,000 a kilogram. So imagine, you say worth its weight in gold. Imagine this gigantic thing made out of solid gold. That's basically what it costs just to put that thing in orbit. Now, it's worth it, right? Because it's pretty cool to see the rover on Mars. But it's expensive. You can understand the scale of the resources that are required to do this. So what are we interested in, and how is this going to make things better? We're interested in small satellites. We see small satellites as the enabler for space exploration, because if you look at this chart and you see there's that big rover there. This is one that's even bigger. This is called the James Webb Space Telescope. These are the big flagship missions that NASA does. But we also have the opportunity to build these little satellites. Here's one that might even fit in your hand called a Cubesat. And we operate in this domain. So we have this plot here that shows mass, the size of a satellite. We have the cost, and you see millions of dollars going up exponentially. And we also have time. This is interesting. Big missions take longer to do because they're more complicated. They cost more. If we operate down here in this small satellite domain, we can do the missions really fast and for a relatively reasonable amount of money. You might say $1 million is a lot of money, right? It's a lot of money to me and you. But in the space business, that's not a lot of money because it's so expensive to do these bigger missions. You can literally do 1,000 of these little missions for one of these big missions. So this is the dimension of our satellite. Like I said, I can hold it in my hand. And this is a model of what one of our satellites look like. I want to show you to scale what this is. Here's the Mars Curiosity rover. This is a big thing. This is about 15 feet across, 4.5 meters, 9,000 pounds with the aeroshell and everything on it. This is our satellite, right? I'm holding it in my arm. It's like the size of a loaf of bread or a football or whatever you want to use your favorite analogy. This is it to scale. Put that satellite, I mean, see the difference? I could put 10 or 20 of these on this mission, and this satellite wouldn't even know. I mean, they would just be packed in around here in all the spare nooks and crannies, right? So I could go to Mars with my rover, and I could take like 5 or 10 of these guys along with me as little probes or something. how much can you do with something that small? Well, I want to ask you to do something that we normally don't do in our talks, right? In fact, they told you not to. Take your cell phone out and wave it around. Everybody do that, right? Everybody's got their cell phone on them, right? This is a satellite, right? This is almost a satellite. Why? Well, this is one of our satellites. Our satellite has certain things that it needs to survive. It has a battery. Your cell phone has a battery. It has a radio. Your cell phone has a radio. It has a camera to take pictures. Your cell phone has a camera, so you could take a selfie. You could say, flying this in Earth, we're going to take a selfie from orbit. It has a few other things. It has an enclosure. It has a GPS. Your cell phone has a GPS. There's not a lot of difference between this and that, except this is really packaged to survive in space. So can you do a lot of things with your cell phone? Yeah, I think so. I mean, imagine being stuck in a parking lot. This is a great way to pass the time, right? You can do a lot of things in something this size. In fact, the idea of launching a satellite into space is not a new one. NASA's already done this. Haven't you always wanted to take your satellite or at some point and just chuck it into space, right? Or kick it into space? And NASA has too. And they've actually built a satellite called PhoneSat. And so this is not a real image. But here's a phone satellite, and this is what it actually looks like. It's been repackaged into something, this size called a Cubesat size I was showing you. And this is an actual image. Now, it's kind of blurry and pixelated, but there's the horizon of the Earth. This was taken with a cell phone, with cell phone electronics, and beamed back to Earth. Pretty cool that you can do that, right? With something the cost. That is a little more expensive than your average cell phone. But, that's still pretty inexpensive in the space business. Now, this low-cost way of getting into space has actually led to a lot of commercial initiatives. And I want to show you a story that was done by CNN actually just this week. So if you can go ahead and play that in the back. This was on CNN this week. You can look it up.
Many of us don't understand that the internet is a luxury. Billions of people around the world don't have access to the internet. So the next big thing is trying to connect the world. One company that's getting a lot of attention recently is called the Outernet. They're going to beam internet access from space. It's a big idea, and how they want to do it is through a very small technology called Cubesat. Essentially what they are these tiny satellites. They hitch a ride with NASA, they go to space, and they can do all sorts of things. There's small technology that really is for testing, for experimenting. With Outernet, they want to broadcast the internet. So I should say parts of the internet. Look at it as if it was the radio, right? They put out certain music and you get to listen to those songs. So they want to do the same thing but with certain websites. This is hard to turn into a reality because you need a lot of money to do this. You need a lot of technical backing. Another issue, or you can beam the internet from wherever you want, but if someone doesn't have the ability to receive it, then you're back to square one. These guys aren't the only players in this space. There's a company called Iridium, and they build sat phones, and they just launched something very similar to this. Google, huge tech company, they have something called Project Loon. They actually launched 20 balloons into the sky in New Zealand, and they were beaming internet to groups of users on the ground. And they said this is just the beginning. So the idea that you could beam internet from the sky, it's ambitious, it's a huge technical underpinning, it's going to take a lot of money to make it happen, but it really represents what is one of the most pressing issues in our society today.
Okay, so they were showing the satellites that were this size. And so the satellites that we're building, and we've been building for several years now, are really kind of going mainstream. I mean, this stuff is going to happen. It's going to make lives better for people around the Earth. They were talking about beaming internet as a commercial product, but what other kinds of missions can you do with something this size? And it turns out that you can do a lot of things. Pretty much anything you could do with a bigger satellite, you can probably do with a smaller satellite on some scale. So, we can look at the Earth. We can do things like, there are a lot of things that it makes more sense to study from space, like a hurricane. It's thousands of miles in size, so it's easier to see what's going on from space if you want to understand the big picture. All kinds of, Earth science. Also, we can look out into space. This thing that looks like an eye is actually an old star, which has blown off its outer layers of matter, And you can see this happening with the telescope. This was taken with now these were taken with big satellites. Maybe the science is going to be different or as more limited by being small, but it's also going to be a lot less expensive. And potentially, in some cases, if you fly a bunch of these and they work together, it can potentially be better. So we can prove out new technologies. This is something called a solar sail. I'll talk about that in a minute. You could fly new instruments. You could prove things out on a small scale to show that they work and then scale them up to bigger missions after you've kind of demonstrated the proof of concept. You can have multiple satellites working together. Here are a bunch of satellites kind of like buoys out making measurements collectively to show something that's happening over a larger scale. Here are some robotic operations where one satellite is flying up to another satellite and maybe repairing it, doing something with it. And if you can do anything at the Earth, why not do it somewhere else like at Mars? If you're going to have a Mars lander like the one I showed you, it wouldn't have been much for them to have put a few of these small satellites on there, and they would have had basically a free ride to Mars. And from there, you could go, image the moons of Mars or something like that that you wouldn't be able to do with the main ship with one of these small satellites. So now I want to talk specifically about our lab and what our lab is doing. These are missions that have been funded by our lab, funded by government agencies to our lab. And you can see our sponsors are NASA and the Air Force. And this is a timeline. When did our lab start? About 10 years ago. These orange lines have been launched into space. These are satellites that have been flown in space. These green lines are ones that are currently ongoing. And first of all, you see there's a lot of them. We're really busy right now. But also, you notice the green lines are getting shorter. The lines are getting shorter over time. And this is because we're sort of improving our capability to design and fly these satellites in a short amount of time. In fact, this mission RACE, the project just started a year ago, and we've already delivered the satellite. So I'm going to tell you a little bit about these satellites. The first one that we worked on was called Fast Track. We love long acronyms like NASA does, right? So we have these long names, and the names aren't that important. But the satellite is actually two satellites, and they get launched into space, and they separate on orbit, and then they communicate with each other. And this plot here, this is them actually being launched. That's also that picture I showed you at the beginning. This is our team that did the ground station that operated the satellite. And so we actually commanded the satellite from here on campus. And these green dots are all the cross-linked measurements that we got between the two satellites. So the satellites are talking to each other, telling each other where they are. And when we first proposed the mission, there was a lot of question about would this even work? And could you also do it for this kind of money, which is not a lot of money in the space business? And not only could we do it, but we did do it. So a lot of critics who were saying, students can't build a satellite, it's too complex. These satellites are still operational today after 3 years in space. I also want to say that this was the winner of the University Nanosat program, which is a competition that the Air Force sponsors between universities held every 2 years. And the first time we entered, we won it. It's fun to talk about where people go and how you actually become an aerospace engineer. This is a team that tested our satellite. You can see a design of our satellite in a vacuum chamber. They went down to Johnson Space Center to test this. These are all students. They're all undergrads at this time. And that was in 2004. That was a while back. Where are they now? Well, I think this is really interesting. They're all aerospace engineers. So every single one of them became an aerospace engineer. So if you want to be an aerospace engineer, how do you get there? You can do these kinds of things in college, and then that leads you to a career in aerospace engineering. I also think it's interesting where they went. About half of them went to NASA, different parts of NASA. Emily here actually worked at JPL for a while. So they went to all the different NASA centers, not just in one part of the country, but all over the country. Maryland, Texas, California, Colorado. Several of them got PhDs, so they went on to get PhDs. Some of them went to work at companies like Lockheed Martin. And some of them formed their own companies or became a partner of a company that was just getting started. So you see a lot of entrepreneurship in this group. And 2 of them got married, They say adversity brings people closer together. So the next satellite is called Lone Star 1. This, again, is a satellite you can hold in your hand. And this is the satellite that was built by our students. And it was launched from the space shuttle in 2009. So here's the satellite being held by one of the 4 students that built it. It's a project between the University of Texas and Texas A&M. Each university is building one piece of the satellite. And this is our part because it's called Bevo, which is our mascot. And that's the Texas A&M part. Our part looks much better, right? We have more burnt orange on it. And there they go. They're going out of the space shuttle. This is like a jack-in-the-box thing. They just open the lid, and this goes. And the space shuttle doesn't even exist anymore, right? This is kind of sad. But there they go. And this is a picture taken from the space shuttle of our satellites going off into space, and there's the limb of the Earth. That's really cool. That's not science fiction. That's science fact. That's actually part of a series of missions ultimately to have the satellites work together and even maybe dock where they fly apart and then they come back together. Because if you can do that, then you can build things in space and do this autonomously without humans being involved. So this is we call this a concept of operations. It shows all the things we're going to do. This is a second set mission that is going to launch in 2014. That's this year. That's not far away, right? So look for it in the news when it happens. This is the satellite that we've built, laying on our table. This is us kind of showing the satellite to our managers. These guys have paid for us to do this work, so they're looking at us very seriously. And this is the real deal. We're really flying satellites that our customers, you think of the government agencies as our customers, are paying us to build and fly in space. This is the mission I was telling you about that we did quickly. This is called RACE. It stands for Radiometer for Atmospheric Cubesat Experiment. And let me tell you a little bit about what a radiometer is. The radiometer is an instrument provided by NASA's Jet Propulsion Laboratory. They found out about the work we were doing, and they were like, hey, would you guys build a satellite to help us test an instrument? We're like, sure. Are you kidding? We'd love to. And so they provided this instrument. What this does is it looks at reflected light from the Earth. So the Earth gets light from the sun. It reflects some of that light back out into space. But some of that light has been absorbed by the Earth's atmosphere, and it's absorbed at certain frequencies based on the molecules in the atmosphere. So we can actually study the Earth's atmosphere with this instrument because we can look at what's been absorbed and what the energy levels are, and we can see, well, there's this much of that chemical in the atmosphere. And this particular instrument is designed to study water vapor, so we can actually see how much water is in the atmosphere. And this is not our experiment, but this is a result from a mission that flew a radiometer. And so you can see the kind of science you get back. This is telling you where all the water is. You use it a lot in the tropical regions. This is our team that built the satellite. This picture was taken on Monday. This is literally last week. We've delivered and built the satellite. This is the actual satellite. It's beautiful. A lot of burnt orange. Got our little logo there. This is what you can do when you get to build your own satellite. This is our customer. This is the guy from JPL. He's pretty young too, right? A lot of young people working in this area of small satellites. And that's our satellite, his satellite. It fits in a suitcase, right? We handcuffed him to the suitcase when he left. And he's got a big smile on his face because he's happy because he got his satellite, right? And so this will be launched into space pretty soon. The satellite looks really pretty when it's all together, but it doesn't, that's the last result. We have to do a lot of work. This is where the engineering occurs to get to that point. So here's what our satellite looks like when it's taken apart. We've taken the solar panels off the cover, and you can see the inside. And now you can see the model, right? This is the same satellite. This is the model of that satellite. And this orange part that I'm holding up, that's the radiometer that was provided by JPL. And the rest of it, this kind of white part, is the rest of our satellite, which does all the communications and survival functions and everything that the satellite needs. Software is a big part of our satellite. Here's our software engineer doing a lot of coding. I love this picture because there's just spaghetti wires going everywhere. This is how development really happens, right? It's not all clinical. And here we are working on the satellite, trying to get things to fit together. Here is a beautiful shot, close-up shot of the kind of workmanship that our students are doing. This is completely built by students. Every wire in here has been designed to have a certain purpose. Even the screws have to be tightened to just the right precision, and they're glued down, because if a screw comes loose in space, what happens is it floats around. It can create a short, electrical short, create all sorts of problems. So amazing attention to detail. Another mission we are working on is called Armadillo. What I want to impress you with is the diversity of these missions. Every mission is a different story. This mission is one where we're studying space debris. If you've seen the movie Gravity, I want to tell you, first of all, that we are not going to have any big natural disasters like they had in Gravity. It's not going to happen. There's no scientific basis for that. That's just kind of set up to give you the story. But we do want to study space debris. We want to understand it because there is a lot of it, including man-made and natural. There's actually a lot of natural space debris. This satellite has an instrument provided by Baylor University that will study space debris from space. This is another winner of the NanoSat program. This is a national competition that all the best universities, if I told you their names, and I'll spare them, but you'd recognize all their names, and we beat them all out. And we've beat them out twice now. In fact, we're the only university that's ever won twice, so I'm very proud of that. And this is our team building the satellite. Ultimately, this is about people, right? This is the people that do the work, and that's what's really important and great, gives a lot of meaning to what we do. Here's our project manager accepting the award, and this satellite will fly in space within a year or two. Inspire is another one. This is one that JPL is doing to go to beyond Earth orbit. So we're going to take these little satellites and we're going to get them all the way out beyond Earth orbit. We can do that again because they're small. It's easier to do that than with a much bigger satellite. This is a team doing this mission. This is about 5 organizations working together. Our role is the thruster, which goes on this satellite, which I can hold it up for you. And one of the big innovations we had, this is a model of that thruster, one of the big innovations we had with this thruster is we make the tank out of 3D printed materials. So this is a 3D printed thruster, basically. So here's the thruster being built in our lab. This is a design in SolidWorks, if you know what that is, that we made. And then this is the real thing. Pretty cool to see that. It actually looks like the design. Amazing. This is the premise. This is just an example, but we have a compressed liquid which expands out and evacuates out, and that becomes the thrust that we use. There's actually no chemical reaction. It's just under pressure. Here's the 2 models of the thruster. Here's our satellites that it will go on. Very cool. Here's a GPS receiver that we flew on a sounding rocket. Here we're studying an aurora. We're looking at the aurora in the sky. We're launching our satellite into the aurora. And this is what's really cool. With GPS, you can actually measure what they call the ionospheric delay. This is how many electrons are between you and the thing you're looking at. The GPS satellite is up here somewhere broadcasting down. You can measure that. So we looked for the aurora. We launched our GPS receiver into the aurora, and we actually got this data back. And you see this big spike here at 100 kilometers altitude. This spike is the aurora. These electrons being absorbed is where the aurora is occurring. So we actually can see the aurora in the data that we collected. We have a lot of other engineering and science problems we have to solve. One is pointing the satellite. We have to make the satellite point in the right direction. We might have things on the satellite that we want to keep in the field of view of, say, the sun, because it tells us where the sun is. We might have things we need to keep out of the sun. And we need to find a path from one direction to another if we want to rotate our satellite that doesn't violate any of those constraints. So we have mathematical algorithms. This is a very computer science, math-oriented problem to tell us how to move the satellite so that we don't violate any of those constraints. You know, the next thing I want to tell you about is almost like science fiction. It's really cool that this can be becoming reality. The idea here is to use the sun's own energy to propel your satellite. This is called a solar sail. So everybody knows what a sail is on a spacecraft, where the sail is being propelled by the wind. In this case, we have just photons of light bouncing off this really thin sheet and propelling the spacecraft by transferring some momentum to it. Very small amount, but if the satellite is light enough, and again, making it small is the advantage here, then you can actually move your spacecraft around this way. You don't have to take any propellant with you because it's coming from the sun. You know, what are we going to do in the future? Looking ahead, we imagine these small satellites working together. Individually, they're small, but they, you know, if we can maneuver them around, we can potentially build structures in space. You know, the next big telescope after James Webb probably won't be launched in one piece. It will be assembled in space. And so that's the direction we're going with this small satellite technology. So today is Explore UT. There's all kinds of amazing things around campus. We have just upstairs in the student activity ballroom, we have a lot of really cool stuff. There's a planetarium that has shows that you can watch. You can build a rocket and launch it. So I built one earlier. So I've now launched a rocket, and you can do that too. And all kinds of cool, fun things upstairs. Also, I'd invite you to go over to the aerospace engineering department, which is on 24th and Speedway. And a lot of also very similar interesting activities, including our lab, is giving a demo. So thank you for your attention, and really enjoy your day, and I hope you have a great day.
Dr. Lightsey will be answering questions, so if you have to leave, please be really quiet without talking so that we can hear the questions for people who are going to stay and hear the questions and answers. So go ahead and pick whoever you like.
Sure. So the question is, what is the definition of a satellite and what is the main purpose of a satellite? And you know, it really depends on the satellite. Satellites serve all sorts of purposes. Some are scientific, like there's an experiment they want to study to understand the Earth. Some are commercial. People want to image the Earth or do things that they would actually pay. Communications is a big one. You know, your satellites provide a lot of the communications that occurs across continents and things like that. And you know, what is a satellite? I think we've seen today several different kinds of satellites, including manned ones that carry people and unmanned ones that are like robots, basically.
That one that you don't carry the device?
Yeah. Now, this one in particular, what its mission was it is a radiometer. So this orange thing is what we call the payload. This is the instrument, and the job of this is to study the Earth's atmosphere. But you know, I showed you about 4 or 5 different missions that we either have worked on or are all working on. They all have different experiments. Well, one of them was to have 2 satellites communicate with each other in space. Another was to have 2 satellites maneuver relative to each other so one could dock to the other one. And another one was to study space debris from space. So we have an instrument on the end of one of them which is looking out to see how much space debris is out there. So, you know, the missions really change based on who the customer is and what they want to do. That's right. Yes, over there.
Thank you. I just wanted to know what is the lifetime of one of those satellites?
Sure. What is the lifetime of one of those satellites? That's actually a really good question. So it depends. If you deploy a satellite like this from, say, space station, and that is the most common way you would actually get something like this into space. In fact, space station has just in the last 6 months launched about 60 of these from space station. So they launch a supply vehicle up to space station, and these satellites are in the supply vehicle, and they shoot them out of space station. And from there, because you're at pretty low altitude, remember we talked about that, there's still some atmosphere there, even though it's very thin. And the life of a satellite like this will be less than a year. It'll take about a year for its orbit to decay, and it will then burn up in the atmosphere. It's so small that it does not pose any risk. It's not like this is going to fall on somebody's head. It'll burn up just like a meteorite would. But if you go a higher altitude, you know, the lifetime can be a lot longer based on how long the orbit lasts. Yeah.
Has anybody launched any living things into space on these micro
Sure.
satellites?
Well, first of all, astronauts are living, so I hope. That is, yes, definitely. But also people are very now and more so, I think, becoming interested in bioscience in space. And so there are missions where they take cultures of yeast and bacteria and things like that up into space, and they watch them grow. There have been a lot of space shuttle missions where they would take ants and things like that up and have them build an ant farm in zero gravity. You remember, it's not zero gravity, but it is weightless, right? They're floating. So a lot of animals and plants, they use gravitropism, the direction of the gravity vector, to conduct their daily lives. And you take that away, they can't function normally. So those are really interesting problems to solve. And then the astronauts all make jokes about, like, well, what happens if all the ants get loose in the space station? They have to worry about stuff like that.
Could you repeat the question?
Yes. So, yeah, and that question there was, are people interested in organisms in space, right?
I guess I meant more from the microsatellite point of view.
Yes, microsatellites. And so the question is, can you would you put a biological payload on something like this? Absolutely. There's some advantages to putting stuff in space that you couldn't do on the ground, like if you wanted to study its response to radiation. There's a lot more naturally occurring radiation in space than there is on the ground. Yes?
Since the Webb is going to be, 1.67 million kilometers away, and we don't have any way to fix it if there's problems.
Webb telescope.
Any plans to use, would it be possible
Right.
to get a small satellite out?
Right, sure. So the question was, could we use small satellites as a way to repair other satellites like maybe Webb telescope, which is going to be a long way away from the Earth, because Webb telescope has to get far away from the Earth to be able to image the stars that it wants to look at. So the answer is absolutely yes. You could do that. Now the question is, the issue today is, I would say, the technology to do that we don't really have. This is what we are developing in our lab, because in order to make these devices very reliable, I mean, normally you wouldn't want this device anywhere near your $5 billion space telescope unless you're 100% certain that it's not going to crash into it or do something like that, right? So you want the technology to maneuver this little guy to be extremely robust and reliable. And that's what we're involved in. That's actually what our research is about. So that in the future, because I don't think you could do this today, but maybe not far, 10 years in the future, you could repair satellites on orbit or refuel them or something like that. You could think of this guy as carrying a gas can. You just fly up to another satellite and refuel it. So instead of having to build a whole new satellite, you can just kind of double the life of your existing satellite. Yeah. Yes?
Satellite traffic a big issue?
Is satellite traffic? Right. Is satellite traffic an issue? You mean like space debris? Yeah, collisions, things like that. So, like you saw in the movie Gravity, I mean, people are concerned about space debris. And it is true that there is a lot of space debris. It is true that it tends to go into certain preferred orbits like space station because, we have a lot of stuff going up to space station all the time, and so we get more debris in the neighborhood of space station. But I believe that space debris is a manageable problem. I'm not really worried about space debris making space unusable or anything like that. First of all, space station, as we said, is kind of still in the outer layers of the Earth's atmosphere. And pretty much anything at that altitude, if you don't do something to keep it in orbit, it will fall down on its own. So, but yes, NASA has had to actually maneuver space station because they were concerned about nearby debris and things like that they detected. So, it's an ongoing issue. It's an issue that's going to have to be managed. But I don't see it as something that we should stop exploring space because we're worried about space debris.
Last question for Dr.
Yes.
Lightsey.
What's your lab going to do next?
What are we going to do next? Yeah, great question. So first of all, we have 3 or 4 missions, as you saw on our plate, that we're trying to get those missions done. One of my quotes that I beat my students over the head with is, you're only as good as your last mission, right? So people are only going to remember the last mission we flew, and we want that mission to be a successful mission. So our focus right now is on getting those 3 or 4 missions completed successfully. They're all going to fly within the next couple of years. I mean, it's amazing how fast things will start happening. And I don't know yet what the next mission will be. It might be an interplanetary mission. There's a lot of cool ideas. And we want to do a good job on the missions we have so that we have people coming to us asking us to do other things.
Well, if some of you still have questions for Professor Lightsey, I'm sure I'd be happy to stay here a little while and answer them one-on-one. But for now, let's thank him for his amazing talk.
Thank you.
All right, enjoy your day exploring UT.
Space, the final frontier. These are the voyages of the Starship Enterprise, its continuing mission.
To explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.